Hello, so today we will continue with Chapter 2, and we'll look at Sections 2.4. We're going to talk about Venn diagrams with three sets. So when we have three sets that overlap, there are 8 different regions that are created. So when you look here, I have them labeled with the lowercase a, b, c, d, e, f, g, and H. So those are the 8 different regions that we're going to talk about. So first what we're going to do is we're going to talk about some ways that we could describe these regions. We are going to use the symbols that we had before, which were intersection, and this was and then union, and this was or. So those are the two main ones that we'll talk about right now. And then as we continue, we'll look at some complements, we'll look at some differences, but the big ones that we'll focus on here are intersection and union. So what we're going to do is just kind of translate some of these intersections and unions into words, and then from there we can look at what regions are included. So again, the regions are the lowercase letters, right? The sets are the capital letters, A, B, C, and then our universe, U, right? So for the first one, this is A intersecting B intersecting C. So if I was to translate this into words, this would be what's in all three. So I'm looking for what's in all three of those, right? What's in the overlap in A and in B and in C. So when I look for the thing that's in all three of them, that's just that one there in the center, which is region E. If I look for what's in A and B, so now I'm not saying that it must be in C, all I'm saying is that it must be in A and in B. So in A and in B. So when I look at this, I'm looking for inside of A, inside of B, and so now we get both of these regions, B and E. So similar to that would be A intersecting C. So, this should be an in. So A intersecting C would be in A and in C. So I can do something similar here. So again, I want to be in A and in C. So A is here, C is here, and so I get D and E. And then B intersecting C, again that means in B and in C. B intersecting C, B is here, C is here, so that would be E and F. So now this looks kind of like a mess, so I'm going to erase some of these lines that we did for these intersections and circles so that it looks clean again, right? Okay, so that's an intersection, right? So now let's talk about a union. So when I look at a union, this is my or, right? So this says anything in A or in B. So this means all of the things that are in A or all of the things that are in B, right? So when I look at this, I'll come back up a little bit here. All of the things in A, all of the things in B, when I write them, I do not overlap. And so when I look at all of that stuff, that will be A, B, C, D, E, and F. So intersection, only those things that they have in common, in A and in B. Union, all of the stuff in A or all of the stuff in B, right? So an intersection should be the same size or smaller. A union should be the same size or larger, right? We talked about that in the previous section. So now if I'm going to do A union C, that means all of the stuff in A or in C. So again, A, B, D, and E. This time I want C, so D, E, F, and G. So my answer there would be A, B, D, E, F, and G. So then similar for B union C, in B union C I've got B, C, E, F, and B, and then in C I've got D, E, F, and G. So B union C in B or in C would be B, C, D, E, F, and G. So now for the last one, we have a complement here, right? So this again is our not. So this says not in A or B or C. So I do not want it to be in any of those things. The only region that I have that's not inside either A or B or C is the region H. So that's outside of everything. So these are just an illustration of some of the ways we could ask for regions of a three-set Venn diagram. What we're going to look at now is how we can shade it and ways that we can decide what parts belong to the shading. So when you want to shade a Venn diagram, there are multiple ways to do this. So if you're good at just like looking at it and understanding what it says, that's totally fine. You can do that. But if you're like me and you need a little bit more structure to what you're doing, an easier way is to use those regions to make sets and then use the operations for sets that we had done previously to see what belongs to what's left, right? So again, if you're good at this, you could say B union C. So B union C would be all of this, right? So that's the B union C. Now I want it not inside of that, right? So I want it outside of this, so not here and not here. And then I want it and intersecting inside of A. So I want it not in B or C, but inside of A, which would leave me this region right here, so the little A, right? So that's one way you can do it. And some of them are simple enough that you can do this pretty easily, right? But let's show you the other way that we can do this. So the other way to do this is by listing out the sets, right? So my universal set here is going to be all of my regions. So A, B, C, D, E, F, G, and H. So that's all 8 of my regions, right? So now I need set A. Inside of A, we have A, B, D, and E. I have set B. Inside of set B is B, C, E, and F. And then I have the set C. And inside of C, I have D, E, F, and G. So now that I know my sets, now I can do my order of operations, right? So order of operations says that we're going to do B union C first. So B union C, all of the stuff in B, all of the stuff in C, all together in one new set would be B, C, D, E, F, and G, right? So that's all 6 of those. We don't write the ones that overlap more than once, right? And now I'm going to do the complement of that. So B union C not. So again, the complement is everything in my universe that's not in the set, right? So I'm going to look at my universe. I'm going to take out the B, I'm going to take out the C, I'm going to take out the D, the E, the F, and the G. And so when I take out those 6, all that I have left, we're going to take out B, C, D, E, F, G, is A and H. So those are my only 2 left that are not in B union C. And now I can do my last portion of that. So the last portion of that says A intersecting B union C complement. And so now I'm going to look at A. And I'm going to look at my answer here. And I'm going to say, what do they have in common? And the only thing they have in common is A. And so again, the only portion that gets shaded over here is that portion which is just the A. So the answer is that portion that is shaded. So let's do another one. This one is usually a little bit trickier to do just by thinking about it, because we have a lot of complements here. We have intersections inside, unions outside, and so this can usually get trickier for people. So I'm just going to rewrite my universe and my sets. If you already have them on the paper, you don't need to rewrite them. So again, my universe, A, B, C, D, E, F, G, and H, and then I had A, which was A, B, D, and E, and then I had B, which was B, C, E, and F, and then I had the set C, which is D, E, F, and G. Okay, so here we go, order of operations again. All right, so order of operations, say I go inside the parentheses first. That's my intersection, but before I can do the intersection, I have to do the complement. So we're going to start with the complement of B. So again, this is everything in the universe after I take B out, right? So B is B, C, E, and F. I'm going to take those out, and I'll be left with A, D, G, and H. Now I can intersect that with C, right? So now we're going to go not in B, intersecting C. So I'm going to look at these two, and I'm going to say, what do they have in common? And when I look for what they have in common, they both have a D, and they both have a G. And so that's my intersection of those two. Now I need the union with A complement. So again, before I can do that union, I need to know what A complement is. So complement of A, everything in the universe that's not in A. So in A, we have A, B, D, and E. So what's left there would be C, F, G, and H. And now I'm going to union these two things together. So I'm going to look here, and A complement, union, B complement, intersecting C. I'm going to put these two together, again without repeating, so I've got C, D, F, G, and H. C, D, F, G, and H. So C, D, F, G, and H. So when I shade all of this, not inside the E. This would be my answer. It would be all of this shaded. So the only parts that are not shaded are the part that's in A and this little like crazy looking Pac-Man type thing, right? That's the only part that's not shaded. The answer is the shaded parts, right? So the answer is all this part that we color. What's left is the part that's not included. Okay, so now that we have an idea about how to shade sets to look for answers, let's talk about the word problems. So when we are dealing with word problems and Venn diagrams, the easiest thing to do is always try to find something that we know all three have in common, so we can start in the center, or something that none of them have in common, so we can put that on the outside, right? Those are the two easiest ones. Once I know something that all three of them have in common, then I can work my way out through the Venn diagram, right? So the big thing here, a survey of 500 people determined the following results about their exercise habits. 242 participate in aerobics, 278 participate in weightlifting, 298 participate in running, 167 in running and weightlifting, 118 in aerobics and weightlifting, 125 in aerobics and running, and 75 participate in all three. So this is where we'll start with our Venn diagram, but the actual first question it asks is how many people are in our universal set, right? So the universal set is only the people in question. So we're not talking about all of the people in the world that exercise, right? We're only talking about those people that we surveyed. So how many people are in our universal set? 500 people. Now I can draw my Venn diagram. So my Venn diagram, I have my universal set, U. I know that total inside of here should be 500. And then the hardest thing about drawing a Venn diagram is making sure to give yourself enough room in the overlaps to write the numbers, right? So we'll call this one my A for aerobics, and then we'll have W for weightlifting, and then down here we'll have R for running. The order is not really important, like which way you write them, right? The numbers will still go in the same spots. You'll still get the same answers, but if you want it to look like mine so that you can follow along, that's how you'll want to make it. So again, we're going to start with those 75 people that did everything. So those 75 people that did everything go right here in the middle. The hardest thing about Venn diagrams is being careful with words like only or not or but, not, right? Those things are limiting words, right? So look for limiting words. If there are limiting words, then we're going to have to be careful with what portion we assign a number to. If there are not limiting words, then we're going to have to subtract things from those, right? So after I get those 75 people in the middle, now we're going to look for ands, right? The overlaps, the intersections of the two. So I have aerobics and running. I have aerobics and weightlifting, and I have running and weightlifting. So these are all my intersections, my ands, right? When I look at these, I'm going to say, do they say not or only? So those would be limiting words, right? If I said they participate in aerobics and running but not weightlifting, or if I said they only participate in aerobics and running, that's different than when it says that they participate in aerobics and running, because now I'm including everybody. I don't care if they lift weights or not. All I care is that they do aerobics and they run, right? So when I look for aerobics and running, aerobics and running, I'm talking about that whole kind of like ovally football looking shape there, right? So I'm going to take those 125 people and I'm going to subtract the 75 that are in the middle. And when I do that, I end up with only 50 people that do aerobics and running, but not weightlifting, right? And so then I can work my way up from there, because again, with aerobics and weightlifting, it doesn't say not or only, right? So this is all of the people that do aerobics and weightlifting. So again, I have to subtract those 75. So I have the 118 minus the 75. When I do that, I get 43. Aerobics and weightlifting would go here. And then again, similar thing with running and weightlifting. I'm not saying only or not, and so that means that I'm including those 75 people in the middle. So I have to say 167 minus 75, and that leaves me 92 people that only do running and weightlifting. So similar to that is the next portion, because in these, I'm talking about people that do aerobics, that weightlift, or that run. It does not say they don't do anything else, right? So again, I'm looking for, do they say not or only? They don't. So this is all of the people that do aerobics, all of the people that do weightlifting, and all of the people that run, right? So all of the people that run is the entire green circle. So that means for running, I have to take those 298 people and subtract any other number inside the green circle. So inside the green circle, I've got the 50, I've got the 75, and I've got the 92, and so that leaves me people who only run at 81. Okay, so now we're going to go weightlifting. Weightlifting was my blue circle, so all of the people that weightlift are 278, and then I need to get rid of any other number inside that blue circle, so 43, the 75 in the middle, and the 92, and that leaves me only 68 people that lift weights. And then for aerobics, same thing, entire purple circle, entire purple circle. And so that would be a total of 242 people. Eliminate all of the other numbers in the purple, and so that would be 43, the 75, and the 50, and that leaves me only 74 people that do aerobics. So now that we have the Venn diagram mostly filled out here, the last thing that I need to know is in the universal set, how many people are left, right? So a total of 500 people inside the box, right? So if I want to know how many belong out here, so in the universe but not exercising, basically I would take that 500 and I would subtract all of the other numbers. So 74, 43, 68, 50, 75, 92, 81. And when I do that, I end up with 17 people out here. So now let's answer some questions. I have my Venn diagram. We're lovely. I want to know how many people participated only in aerobics. So we just found that, and we said only in aerobics were those 74 people. Only in weightlifting, those are the people that only did weightlifting. We just found that, and we said that was 68 people. And only in running, those were the greens, right? And we said that was only 81 people. And the very last thing that we did was find those 17 people that were inside my universe. So they took my survey, right? But they didn't do any sort of those, well, they didn't do any of those three types of exercise, right? And we said that there were 17 people who did not participate in any of those three activities. So now we're going to talk about De Morgan's laws. De Morgan's laws are like a pair of related theorems, right? And what they do is make it possible for us to change statements from looking one way to looking another way. So sometimes we may be more comfortable with looking at an intersection than a union, or a union than an intersection, or maybe we don't want to do the complement a lot of times or something like that, right? And so De Morgan's laws are nice. The thing you have to be careful with is this only works for intersection or union. All right, so this does not work for the difference. When we talked about set differences before and we did subtractions, this does not work for that, okay? So this is only going to work for an intersection or for a union. Basically what this is it's a distribution of complements, right? So we have A intersecting B prime, the complement of that, right? And so what we can do is we can take that complement, we can distribute it, we can give it to the A and to the B, and just like when I distribute a negative, that also changes the sign in the middle, right? So I give the complement to both of the parts, and I switch the sign in the middle, right? So when I look at this, the intersection goes to A and to B. So now I have not A, not B, right? And then the middle, my intersection, changes to a union. So both things have to happen. I give the complement to both, and I switch the symbol in the middle, right? So when I do this, there are two ways to look at this. Again, these are small sets, so some people may be able to just look at them, right? So if I looked at A intersecting B is here in the middle where they overlap. So if I wanted it to not be that, basically I would want everything outside of that intersection, right? So I would shade all of the portion outside of that. Okay, so now if we try to do this for not A union not B, now we're going to have to say what's not in A. So if I'm not in A, I'm all of this, right? And then I have to say what's not in B, right? So not in B. And then since I'm unioning it, I want all of the stuff that has any color inside of it. And so we get the same thing. The only place where I don't have either of the colors is that portion there in the middle. And so my answer is all of this stuff on the outside. So this is how we can show that they are equivalent statements, right? That they give us the same answer, because basically all we get left is that little oval in the middle. And so we can say that when I distribute the complement and I change the symbol in between, then they are equivalent statements. This also works for the union. So A union B not. Again, my union here is everything. So that would be like the entire figure 8. All right, that's my union. And basically I don't want it to be in there. And so I want everything outside of that. So now we have to be careful. So again, I have not in A intersecting not in B. So we can do this similar to the way that we did it above. So not in A. All of this stuff. Not in B. Now I'm intersecting. So that means I want it to be both purple and green, right? So if I'm looking for where I'm purple and green, this part's only purple, so I don't want it. This part's only green, so I don't want it. So only purple and green together would be all of this part outside. So again, this is just an illustration to show how De Morgan's laws work. Basically, that they do give us the same answer no matter which way we choose. So now, if you have something written in one way and it's harder for you to see how to shade that, you can distribute that complement, and you can change the sign in the middle, and then you can shade that portion, right? So again, if you do not like how it's written, you can use De Morgan's laws to rewrite it, and that will help you see it easier, right?